On September 26, NASA and partners crashed a spacecraft into an asteroid with the goal of shifting its trajectory. It was all part of its Double Asteroid Redirection Test mission, known as DART, and the first ever test of planetary defense. Lindley Johnson is Planetary Defense Officer at NASA and Program Executive for its Planetary Defense Coordination Office, which funded the DART mission. Lindley, welcome back to the program.
Oh, thank you. Glad to be here.
We had talked earlier when you first launched, so remind us of the DART mission and how it played out.
Well, the DART mission was to test the technology to change the motion of an asteroid in space. DART launched back in November of 21, and it took us 10 months to get to this double asteroid system, and we were to impact the moon of Didymos, called Dimorphos, and change its orbital period about Didymos. And so on the evening of the 26th of September, the DART spacecraft did what it was designed to do, direct hit on Dimorphos, and now our observations post-impact have confirmed that we have changed the orbit of Dimorphos.
So how much has it changed?
Well, the orbital period prior to the impact was almost 12 hours, 11 hours and 55 minutes. And we changed that period by 32 minutes, about a 4% change in the orbital period. So we did prove that this technology could be used.
And how significant is that change? Was it in line with expectations? Did it exceed expectations?
Well, there were a range of what we thought we could expect. There are several variables involved. Composition of the asteroid itself is one of the big variables. We didn't know what that was, so we had a range of compositions that would affect how much the change was. We sort of expected somewhere between several minutes to several tens of minutes, 30, 40 minutes. And kind of the midpoint of our estimates was around 10 minutes. This change was more than that midpoint, but well within the range of what could have happened.
And I know you're still collecting data, but what have you learned so far from the initial data that you've gotten so far?
Some of the images that have been collected by both ground and space telescopes show us the amount of ejecta that was blasted out by this impact. And that was probably more than we expected, which sort of explains why the orbital change was more. You know, part of what happens here is the impact blasts a bunch of material off the surface of the object, and that enhances the momentum change just from the impactor itself. Seeing this ejecta both from ground-based telescopes, we didn't know we'd see that much just from the ground, but also from space-based telescopes, both the Hubble and James Webb telescope imaged after the impact.
Why did NASA carry out this mission to begin with? What's the big picture here?
Well, the big picture is there is still a lot of natural debris from the formation of the solar system, asteroids and comets that come into Earth's neighborhood in the solar system. The Planetary Defense Coordination Office at NASA's responsibility is for finding any asteroid that poses an impact hazard with the Earth and predicting out into the future when that hazard may occur. First of all, our highest priority is finding them and knowing what the danger may be. But then what are we going to do about it? What capability do we have? What technology, space technology that we now have, can we apply to protect the Earth from this type of natural disaster ever happening again? And so that's what DART was about, is demonstrating we do have the technology to change the motion of a cosmic object in space.
Well, let's talk about what could happen. And I know that obviously this particular asteroid didn't pose any threat to Earth, but if one did, what could happen? I mean, would it destroy the entire planet?
No, there are no planet killers out there, and not even any as big as the asteroid comet that was thought to cause the demise of the dinosaurs. There are those of that size out there, but we have now found everything that large and larger. So now we're talking about asteroids that are in the range of a few hundred feet, a few hundred meters in size. Now, an asteroid impact by, say, an asteroid the size of Dimorphos, 160 meters or so in size, about the size of a small football stadium, if it were to occur near a metropolitan area, it would be a disaster on a scale that we've never had to deal with. The blast radius from something that large hitting us at 17,000 miles an hour would cause devastation across a statewide area.
And what was the biggest challenge, Lindley, in this project overall?
Figuring out the orbit of the asteroids, Didymos, and particularly Dimorphos about it, understanding their position in space and the position of the moonlet relative to the asteroid, and then navigating the spacecraft to be at the right point at the right time to hit Dimorphos. You know, hitting a bullet with a bullet doesn't begin to explain the velocities that we're talking about here. So first, building a spacecraft specifically designed to do this mission, and then getting it there at the right time and in the right place.
You know, finally, I'm wondering if you're looking at any other ways of testing how to deflect asteroids.
Well, yes, we are. And we have a list of different techniques that might be practical to use for this type of thing. In principle, anything that will change the speed, the orbital velocity of the asteroid, changes its position into the future time. So anything that you can do to either speed up or slow down the asteroid, and you impart that to it several months to years in advance, then it will arrive at the point in space where it could have impacted Earth either early or late. So that's the whole principle. You just need to change the speed of it just a hair. So any technique that you can think of to change a 2,000 metric ton object in space could be used. So we have ideas like a gravity tractor, ion beam deflector, and a whole list of techniques that might be tested.
And I didn't get a chance to ask you how you felt when it hit, but we'll do that for our next interview, okay? Lindley,
Okay,
thanks
sure.
so much for the interview.
Yeah, you're quite welcome. Thank you.
Thanks for watching. If you enjoyed the video, give it a thumbs up and subscribe to our channel so you don't miss out on any future Government Matters interviews.